Bartosz. And Bartosz, the floor is yours.
Thank you. I'm really impressed that so many of you are here today, even though this is the last day of the summer school. Usually, when I attended summer school, last day I was somewhere else. Yeah. So it is also a great honor to give a talk, and thanks. I would like to thank the organizer for inviting me. And today I would like to talk about a specific branch of my research, which corresponds to prototypical parts. And prototypical parts are kind of methodology that can be used to create interpretable models. So I won't give you a wide journey through all my research, but instead I will just concentrate on 3 papers that me and my team created, which consider this topic. And I hope that I will convince you that prototypical parts are something that is worth to look at, that it's worth to use. So I will talk about 3 papers published on KDD, ECCV, and WACV. And those papers are, well, of course, not written just by me, but by a few other people which are in my team. So here you can see all of them. And this research is mostly done in a group of machine learning research. The funny thing is that maybe some of you wonder what's the shortcut. How's this shortcut? What's going on with the shortcut? It has nothing in common with this name, right? The shortcut should be GMLR, right? But the problem is that the shortcut is from Polish, you know? In Polish, grupa metod uczenia maszynowego. And, well, this is something interesting, in my opinion. But you know, the name is well known in Poland, so it's hard to change it right now. So. Okay. So just a quick presentation. Most of the people are researchers from the Jagiellonian University and PhD students, mostly from computer vision, but we also have a cognitive scientist, Koryna Lewandowska, who work with us and help us from the psychological point of view, because in my opinion, when it comes to interpretability, explainability, we should put more attention into how the human understands this explainability also. So currently we are going into this direction as well. So what's the motivation of explainability? The problem is that deep neural networks are black box models, right? And they return prediction with high accuracy. However, we do not know what is the reason of the prediction, right? Is the reason good, right? So for the given image, like this image of cat, we know that the probability of the cat is 0.97, but the question is it because of the color, which is usually like that in case of cats, right? So we don't know, and we should definitely check it before put this model into words. Okay. What will happen if we won't do it? Well, a lot of current, well, problems of deep networks, of deep learning, are caused by the fact that we did not know what was the cause of prediction. So here you have three articles from different journals, which talked about problems with deep learning. So first, the problem that appears is that people ask, can we trust deep learning, right? And this is very problematic, because if people think that we cannot trust something, they don't want to use it. They're getting afraid of it, right? So even though sometimes, in my opinion, the problem can appear with deep learning, the prediction can be wrong, even then we should explain what it was wrong, right? Like the human would explain it, right? And this is very important. So the Tesla accidents, right? The problems with racist chatbots, for example, right? Or if we use deep learning in jailing systems, for example, they can be very racist also. So we should first train the model, and then we should analyze what stands behind its prediction, and then we should, well, change the wrong causality, the wrong reasons, remove them, right? Either by removing, well, biased sample from the database, or by doing it otherwise. So that's why the explainability appeared, and last year we observed a huge step into this direction. The explainable artificial intelligence, like the shortcut is XAI, wants to cover this gap by introducing not only the prediction, but also the reason of this prediction. So explanation. So there is deep neural network which return prediction, and then we ask why this prediction, and we see the reason, right? In this case, you can see that the reason of classifying this husky as a wolf was wrong, because the model was biased due to the fact that most of the wolf images was made on this with the snow background, right? So snow in the background. So that's why the husky was also predicted as a wolf, and that's kind of model that should be changed, should be fine-tuned, should be retrained maybe to remove this bias. And a lot of methods appear in the literature. You probably know methods like GradCam, which try to explain the model which is already trained, right? So we have a black box model, like deep neural network, and we want to explain it using different methods. So that kind of methods are called post hoc methods. So you have a model which is trained, and you want to explain it using some post hoc method. GradCam is a kind of post hoc method. However, the problem with that kind of method is that they escalate the problem by providing misleading or adding unnecessary authority to the black box model, because their explanations are usually mislead. And there are some papers which one of the example is sanity check on saliency methods from the RIPS 2018, which show that most of the explainability post hoc methods are biased, are not always true, return wrong explanations, which are not accurate. So that was the main reason of introducing interpretable models. Well, interpretable models existed before, right? Like decision tree, right? Decision tree are interpretable models, right? You ask about the feature. Is this feature above the threshold or below? If it's below, you go left. If it's above, you go right, right? So it's quite interpretable. Anybody can, well, analyze it. Of course, the problem appears when we talk about random forest, right? Then there's a lot of trees and it's less interpretable. But in case of deep neural network, there's so many weights, there are so many parameters that, well, the analysis is not so easy anymore. So the motivation of our work is to introduce models which use deep neural networks that are internally interpretable, right? So they contain some kind of component that makes them self-interpretable, like decision trees, right? And this is the main motivation. So to talk about 3 papers that I mentioned before, I have to introduce the basic paper that we started with. And this paper is called, introduced something that is called prototypical part network. And prototypical part network uses something that is well known in cognitive theory, cognitive sciences, that is called case-based methodology, right? There is a cognitive theory that says that humans use that kind of reasoning, like case-based methodology, so case-based reasoning. How does it work? Well, it works like you can see in this image. So you have some set of prototypical parts. It is very important to tell the difference between prototypes and prototypical parts. Prototypes are usually in machine learning literature consider some prototypes which describe the whole image, the whole object, right? So there are some prototypes for each class, right? But here we have prototypical parts, right? And prototypical parts are the parts of the object. So what would be the prototype? The prototype would be clay-colored sparrow, right? Like the prototype of clay-colored sparrow, like the whole bird. But prototypical part considers its different parts, like the head of the sparrow, the legs of the sparrow, the belly of the sparrow, right? Those are prototypical parts, so parts of the object. So there is a cognitive theory, as I said, which said that in our brain, we have some representation of that kind of parts of the object, right? Like the legs of the chair, right? The belly of the bird, the head of the bird, right? And when we analyze new image, we just try to find those prototypical parts on this image, right? We try to check if those prototypical parts exist on the image. And then when we see that specific number of prototypical parts appears, we generate the prediction, right? And that is the idea behind the prototypical parts network. So we will have a prototypical parts considered as a parameter of the model, right? They will be trained together with other parameters of deep neural network, right? And then when we will analyze the image, we will try to check if those prototypical parts exist on the image. So when we return the prediction that this is a clay-colored sparrow, we will also say that we predicted it like that because the following prototypical parts appeared on the image. Okay? Is it clear? Perfect. So the question that is as a follow-up.
Excuse me, we have a question.
So is this only does this network only tell you that n prototypical parts have appeared and that is why a prediction was made, or does it also tell you what the prototypical part was?
Yeah, so in this case, we will have a prototypical parts defined as patches from training set. And we could put those patches into some vision into some model who would describe what is on the image, right? But this is the other problem, the problem of visualization, right? Of the visual concept, right? And this is somehow open. Right now, we'll also only have the patch, but it's not described in any other way.
Sorry?
What's the generalizability of this kind of network? Because what I'm guessing is that if you have prototypical parts for birds, you cannot classify cars, for example. So like, what's the, I don't know, power to explainability ratio in this case? Predictive power to explainability ratio, yeah.
Well, in fact, it was not researched yet, this question, but so I can give you only my intuition. And my intuition is, of course, that if we have prototypical parts of the bird belly, then it cannot be directly applied to other domain.
But like, wouldn't it be intractable to have, I don't know, as many prototypical parts as you would need to classify ImageNet? Wouldn't it be easier to learn more like rudimental features or more?
Yeah. So the main limitation of prototypical part methods, it's till this year it was not applied to database which are not fine-grained. So till 2023, it was only applied to fine-grained database, like the Cube, right, or car database. As I will show you the example of those database in a second. However, this year a paper appeared who also applied it to ImageNet. So I would say that the basic prototypical parts are not sufficient to ImageNet, but there are some extensions who enable it. I will not talk about them today, but I can send you an email with the work.
Thank you.
No problem. Yes? This is for many birds. So it's a cube database with 200 species. So, and each species will have 10 prototypes. Perfect. Thank you very much for the question. How there be more, especially for the for the next slide, which in my opinion would be the most important in this talk. So if you understand this slide, everything else should be, well, quite simple. So to understand how prototypical part network work, you have to a little bit, think about deep neural networks from little bit different perspective. Like there is no final layer which is fully connected as usually, but instead of that there is a prototypical part layer which works in a different manner. So let us analyze how it works. When I first saw this paper, it was very hard for me to understand what is going on there. So let's try to analyze it, and please ask questions if you have. Okay, so the first part of the model is quite simple. It's just convolutional layers, right? Like in the standard neural network. So for the input image of size, I don't know, let's say 500 by 500 by 3, right? The 3 layers, RGB. We push it through the convolutional network, usually called backbone network. And then we obtained how we say the representation, right, of this image. This representation is, of course, the resolution of this representation of the two first axes is smaller, right? For example, 7 by 7, when the input was 500 by 500. But of course, the number of channels is larger, right? And this is standard, right? In standard neural network, we just, make the max pooling, right? So the dimension is smaller, but we extended the number of channels. And the big assumption of prototypical parts method, which, considering my knowledge and all the experiment that we made, is usually okay, plus minus, is that the spatial position on the representation space corresponds or represent the spatial positions on the input space, right? So if we would look on the on this vector on the left upper corner, right, and the vector is like the size of the vector is the number of channels, then it should represent the upper left part of the input image, right? And if you run the experiment of neural network, it's usually true, right? It's hardly possible that this part of the representation, right, the bottom right corner represents the upper left corner, right? This is usually not true. So we have this representation, and then we take those vectors, right? This vector from position 1, 1, 1, 2, 1, 3, 1, 4, right? So all the vector from this representation space, if we have 7 by 7, then there is 49 vectors. And we compare them to vectors which corresponds to prototypical parts. So each prototypical part is also represented by the vector. And the size of the vector, dimension of the vector, is the same as the dimension of the
Sorry, we have a question.
representation, of course.
So where do we get the prototypical parts from?
Well, the prototypical parts are, well, at the beginning, there are like random vector. There are randomly initialized vectors. Okay, so there are trained together with the other parameters of the network.
Also, we have like, for example, the top image of the bird head, that's just a random matrix. And then over time, you keep comparing this to your representation of your current image, and then you also learn the corresponding matrix.
Well, in fact, this training contains two stages, okay? First, there is a random vector which does not correspond to any patch. It's just a random vector, okay? And then, when we train the network, and the network is trained, we replace this vector with the representation of the patch which is the closest one to this vector.
Okay, so we have kind of the prototypical representation, which we then use to extract the relevant thing from the image to which we then compare to?
No. We, maybe it would be simpler. As I said, this is quite complicated, so this slide will take us a little time, okay? So I was prepared to that. But let's look at it like that. This patch is represented by this vector, okay? But you just use this patch after you train the whole network. When the network is trained, right? You have a latent space, and here is your P1, right? This is a vector in the latent space, okay? Here's your P1, but of course, well, it was trained together with the other parameters of the network, right? So it does not correspond to any patch yet, right? So at the last phase of the training, you push all the patches from the training set, and you put them into this latent space. Okay? And one of them is the one which is the closest to P1, right? So you replace P1 with this vector, and for this vector you also have the patch, right? You understand?
I think so, yes. Thank you.
No problem.
And we have another question.
So you said that most of the times the configuration of the image in the representation and in the input space corresponds. But what, for example, if that P1 is catching on the head of the bird, which usually is on the upper part of the image, but there's one image in which the bird is eating something from the ground. Will it be able to recognize the bird?
It doesn't matter where is the head, right? Like the head can be on the, for example, here, right? I only said that this part in the representation space represents this part from the input space, right? But what's there, it doesn't matter. It can be head, it can be legs, right?
So you compare the old representation with all the patches, like in each
Yes.
slide.
Yes.
Okay. Okay.
So if the representation space for image is 7 by 7 by the number of channels, right? Then I compare 49 patch representations, right, with prototypes to see to which prototype this representation corresponds, and to which prototype this representation corresponds, right? I search, I search each prototype on the whole image, I would say. Okay. Sorry for technical problems. Okay, so again, we have representation space, we have prototypical prototype layer. We should call it prototypical part layer, but yeah. And well, if we compare, for example, prototype P1 with each position in the representation space, we obtained a similarity map, right? And this similarity map should tell us in which place of the image this prototypes appears, right? And here, the similarity map is blue if the similarity is small, and high when the similarity is large, right? For example, the head exists right in this part of the image. So we obtained a similarity map, and so the question is how we compute this similarity map. Well, we just take each prototype, right? For each prototype, to generate this map, we take the representation zx for the x, which is the input, and zx is the representation of input x, right? So I would say this is the set of these vectors, 49 vectors, right? And we compute the similarity like that. This logarithm of division maybe looks complicated, but it's quite simple. Because if here on the x-axis we say that is z minus p, then this logarithm would look like that, okay? So what does it mean? It means that if the difference between z, right, so the dot here, the representation of the patch, distance between representation of the patch and the prototype is small, then the similarity is high, right? And if the distance is small, then the similarity is low, right? And it's not linear function, but that kind of logarithm just to put more attention of the similarity, right? Which is close to 0. So this is the logarithm, right? And if we compute this logarithm for each z, right, so for each location from this representation space, then we obtain this map. What's the size of the map? Similarity map? Anybody know? What's the dimension? Seven by 7, exactly. 7 by 7. If the dimension of the representation is 7 by 7, then this map is also 7 by 7. And what we do, well, this is something uncommon or common. We take the maximum value. So to what this maximum value will correspond? What do you think? Most similar area. So the area where this prototype activates most, right? The area to which this prototype is the most similar. Exactly. So if the maximum is high, right, then we know that this prototypical part exists on the image. And if it's close to 0, small, then it does not exist on the image, right? So this is the prototypical layer. And then there's a fully connected layer, which at the end. And this fully connected layer is also made in a specific way. Because for each prototypes, as I said, each class has 10 prototypes, right? So if prototypes P1, P2 are, well, prototypes of this class, black-footed albatross, then the weights here are equal 1, right? From here to here, and from here to here. But other weights from prototype 1 are 0. So this way, inside the network, we have, well, there is a knowledge inside it. We put the knowledge which prototype corresponds to which class using the last layer, right? Last layer tells us about it. This is pretty much everything about the architecture, but you probably have still some questions.
Sorry, you have a question?
So for the last part, what happens when my input bird has like the prototypical parts maximized for different birds? You know, like, so like the neck is like one bird and something else is like other bird. How does the network then figure out what is the output bird?
Well, in the end, you can have well, confusion of the network, right? It can say that with the probability 0.5, it is black-footed albatross, and 0.5 clade color sparrow. Because I have not told about it, this is output logic. But after this, we also have softmax, which finally return the probabilities for each class.
I might not have gotten the difference yet. In a normal convolutional neural network, you have those different layers, different features, basically hierarchy, and the filters. And post factum, you can say, okay, those filters stand for example, you can track, they activate certain features on different level of hierarchy, right? So in a vision, at least, you could explain a prediction based on this combination of triggered filters. So the difference, I see that we learn this parameter matrices here, which maybe facilitate the at inference time this matching, but is there like different, how to say, optimization or different approach? I'm not sure.
Yes, in fact, I think I saw the paper who tried to use features from different layers of the network. As you said, right? On the beginning, on the initial layer, there should be information about the call or simple texture and so on, and there should be more and more information above, but well, higher. The information about higher features, right? Higher feature above. However, either we talked about it, either we saw that kind of paper, but the paper was not significant for sure, and I think it's because it brought additional complexity to the training, which already was already complex. So to answer your question, I think there is a paper who tries to do that, but I'm not sure. For sure, it's not. In the main flow of prototypical parts. Okay, so yeah, so that's pretty much about the architecture, and as I said, it was counterintuitive for me when I first saw it, and confusing. I think that maybe some of you, might have problems to understand it, but I hope that at least some of you understand it. So, no other question to this? Because this is the most important slide, I will say. If you understand this one, then everything would be possible. Okay. So, one more thing. So, why we say that this kind of network is interpretable, right? This question is that appeared to me. Why should we consider it interpretable, and why it is better than GradCam, for example? And the answer is that, well, it's contain this prototypical part layer, which is not some kind of additional branch of the network. It's not something that is there is a network and there is something additional who tries to do it. You can see, who tries to explain what is going on the main flow. This is inside the main flow. So if you want to go from the input to the output, you have to go through the prototypical part layer. It makes, well, it influences the final prediction, right? You cannot obtain final prediction without going through the prototypical layer, right? So when you obtain this final prediction and you have the information about the activation, the similarity to each prototype, then you can show to the user which prototypes were activated, right? So this is the main reason why this approach is considered interpretable. As I said, well, it does not come, nothing comes for free. Their architecture, when we already talked about it, seems to be quite simple. However, it turned out that if we use only cross-entropy cross entropy to train it, then it doesn't work. It obtained like random values, so random predictions. So so the main achievements of the paper who introduced prototypical part network, in my opinion, was not the architecture, but the way of training the architecture. And the training contained two additional loss functions. Except the cross entropy, right? So there was a cross entropy, which we all know how works, of course, but also two additional functions, clustering and separation. So, as I said before, we have this set ZX. This set ZX is the set of all representation of all positions, right? The set from the representation space, the vectors from the representation space. So this D is the number of channels, right? And this H times W is 49, right? So this is 49 vectors. And what do we do? Well, we go through all data from training set, so for all axes, right? And we push them through the network, right? So we obtain 49 or other number, but let's say 49 representation in the latent space. And those representations here are the small dots, okay? The small dots. So I only draw 4 of them instead of 49, because 49 it would be definitely too much for the last lecture of the summer school. Okay, and what do we do? Well, the first function, loss function, clustering, tries to find, well, the prototype of the class of X, which is closest to this to one of the representation of this image. So again, we have X, right, which is an example of green class. There are two prototypes in the latent space of green class. Those are the big red dots, okay? This X is from green class, and this class has two prototypes. So we analyze all the representation of X patches and take this one, which is closest to any of prototypes of green class, right? This will be this dot, right? And we want to attract them together, right? So we want to example of green class be close to the prototypes of green class, right? This is the clustering function. And there is also a separation function which wants to, when here we attract, right? And here, what is the name for, you know, the opposite of attraction? Repel? Repel. Okay. We want to repel the the patches of the green class from the patches of the red class, okay? So we want to be, example of sparrow, we want to be close to the prototypes of sparrow, but far away from prototypes of other classes, okay? And that kind of training resulted in very good results. You can see them here. So, So here you this is the main table from the from this paper, Prototypical Part Network. And well, they compared to the non-interpretability model, which was the best during their research, and the model called the BCNN, right? And this model obtained 84.1 for non-bounding box setup, and 85.1 for bounding box setup. But if they run their method, they obtained very similar results. So the results were only, well, less than 1% worse than the state-of-the-art method trained for cube data set.
Can I just ask something?
Mm-hmm.
I was wondering, when you do the embedding of the prototypes and you try to put them together, do you do that only for prototypes that represent certain things from a given class? So all the wing prototypes for a certain class will be close to the wing patch, or do you do it across all different prototypes for a class? So both wings and head and legs will be together in latent space for the same class.
I'm sorry. Can you repeat the question, because I was not able to localize you and.
Okay, so I was wondering, when you try to push together the prototypes of the same class, are you only trying to push together representations and prototypes of the same object, for example, wings, or do you actually try to push together all prototypes for a class, so both wings and tail and legs and everything else?
Yeah, everything. The second, because we have no information about what is on the prototype, right? This is fully automatic. We only have information about the class. So we have input and the output, and nothing else. So that's also the nice thing in this approach, that we do not need any extra knowledge, right, to generate prototypes. Thank you. The most of the experiments also on our paper were made on two databases. The first one is Cube 200 2011, and the second one is Stanford CART. And I show some of the examples from those databases because it's very important to underline that those databases are fine-grained databases, right? So all of them have either cars or birds, but the different species of different models. And as I said, the authors of Prototypical obtained very good results, considering the fact that they also return the interpretability, right? The interpretation of the prediction. And here you also can see how this interpretation look like for the real world example, right? So it was, well, this image was predicted as red-bellied woodpecker because the following prototypes appeared in the following places. The places can be either shown as the bounding boxes or as a similarity map in this image. And how we visualize it, this is also open question, because first, well, the question is what is important for the model, what is important on this patch for the model? Is it the color, or maybe the fact that it's mixed of red and white? Or maybe it's also black is important. So the concept, visual concept visualization is an open question.
Do I understand correctly that for each input image, the prototypes are going to be different?
Can you repeat?
Will the prototypes be different for each input image?
The prototypes are all the time the same, right? When you have trained model, when you trained the model, the prototypes are fixed. And then you push the input image and analyze which of the prototypes, which are fixed, right, on the inference phase, exist on the image.
Then at what point do we fix the prototypes then?
Hmm?
Because I think earlier you said that prototypes are trained with the network. So I was wondering, at what point do we fix the prototypes to
After the training, right? During the inference. Because, as I understand, you asked, does the prototype are different for each input, right?
Yeah.
And the answer is that there is 10 prototypes per class, right? So if there are 200 classes, there are 2,000 prototypes, right? And each image has some similarity to each of the prototypes. But you can, for example, show 10 which are the most similar, right? And from the point of visualization, you can say that we show different prototype for each image, right? But we, well, to some degree, the image is similar to each prototype, to some degree, right? It's more similar or less similar. This is...
Maybe let me put the question in a different way. So I see here that the prototypes are quite clearly interpretable images from the training data set. But if we start prototypes as random vectors or matrices and we train it, they're not supposed to converge to nicely interpretable images, right? There's still going to be some mess of noise that is not...
Yeah, so here we are going back to this, this question appeared before, right? So let's assume that after training, right, you have some prototype P1 in the latent space, right? And this was trained from the random values, right, at the beginning. So it does not correspond to any patch, right? So what you do on the final stage of training, right? You push all the training patches to the network, right? And you obtain their representation on the input space, on the representation space, right? And the one which is the closest replaces P1. And now you have representation, right?
Got it. Yeah,
Got
thanks.
it? Perfect. Thanks for question.
So one quick question on the computational power. This seems like this scales with the number of classes that you have, which will be very high in some cases.
So the number of prototypes increases with the number of classes, right?
Yes, and the filters also increase with the...
Yeah. So yeah, so that is the main limitation, the large number of prototypes, right? Because each class has to be, well, each prototype is assigned to only one class, right? And it also, but on the other hand, it may happen that some prototypes exist in two classes, right? So they should be shared, right? And this was our first observation. And the first motivation, main motivation for the first paper, Prototypical, which we introduced and published in KDD. So, as you said, right? Here, for example, we have one class, two classes, and each of them has, well, prototype which corresponds to I, right? So instead of having two prototypes in latent space, there should be one, right? Which is shared between those two classes. And then the number of prototypes decreases, right? That is the idea, right? So, So what we did in this KDD paper is that we wanted to share prototypes between classes. And I will in a second say how, but maybe you have a question to previous slides. Okay. I still have, what, 20 minutes, right? 30? Oh, okay. Okay. So the architecture in our method looked very similar. However, as you can see here, the prototypes were shared between classes. So, for example, this prototype 2 was both in class common yellowthroat and warbler. So how we did it? First, we did it in a very like naive way. We first trained Prototypical. So we had 2,000 classes for 200 species. So we did not solve the problem with the high computational power and the fact that we have to generate a lot of prototypes during training. However, we wanted to decrease the number of prototypes to share the prototypes during the inference. So we first trained the Prototypical. We ran the Prototypical in a standard setting, and then we repeatedly merged similar prototypes. Okay, so for example, here, right, we saw that prototypes P1 and P3 corresponds to the same thing, right? And we use special type of metric to analyze the similarity between prototypes. And we merged it together. So we removed 3 and we just used the connection between P1, which before was close to 0 to this class. We changed it to the sum of weights from those 2 edges, right? This edge was removed, so we just add 0.85 to this edge, right? So from this point, prototype P1 was also prototype of warbler. So in the end, we just merged the prototype. Prototypical parts which were similar, considering some metric. And what results have we obtained this way? Well, you can see on this image. So first, let us look on Prototypical, simply trained with different number of prototypes, different number of prototypical parts. So here, all the models were trained with 2,000 prototypes, right? So 200 classes, 10 prototypical parts per class. So we have 200 times 10, so 2,000, right? And the accuracy of the model is around 0.8, as I shown on the slide. But if the number of prototypical parts for class is smaller, right? Here we take smaller and smaller number. For example, when we have 1,000 number of prototypes 1,000, then there is 5 prototypes per class, right? Then the accuracy decrease, especially here, right? When we have only 2 or 3 prototypes per class, right? 500 by 200 is 2.5, right? So it's decreased here rapidly, right? The Prototypical cannot, cannot deal with such small number of prototypes per class. But if we take the protopinet and we just merge the prototypes so they are shared between classes, right? We obtain this blue line here, blue curve here, right? So we can remove much more prototypes, right? And still obtain very high results, right? So each class still have 10 prototypes, but they are shared between them. Okay? Is it understandable? Yeah? And we also tried different approaches, like what would happen if we merge random pair of prototype instead of using our metric that we introduced on the paper. And random does not work well as well, right? And we also use different type of metrics that is orange color. And here is just different backbone networks, right? 2 different backbone networks. We tried 4 altogether, but I decided to show only 2. For other, the trend was the same. So here you can see how, for example, 7 prototypes merged to 1, right? So those 7 prototypes from different classes merged to this one, and those classes were able to work with only 1 prototype. We also show how does it look when we compare the number of shared prototypes. So here we can see that there are 2 classes of sedan which shared 4 prototypes, right, after our methods. But there was none of the prototypes were shared between sedan and Aston Martin. That was funny to observe, right? Aston Martin and Audi, on the other hand, shared some prototype. But still, we found limitations. For example, we required 2-stage training, right? And we also observed that some of the maps were not like satisfactory. So some of the prototypes just corresponded to the background or to the white area, right? And in our opinion, the prototype should be more salient. It should correspond to only one specific part of the object. So what we did, we introduced protopool. This protopool also the main aim of protopool was to share prototypes. However, without this 2-stage training, right? So we wanted to share them from the beginning. We published this on ECCV. So here you can see how it works. It's quite complicated, but I think that the most important to say here is that there is a pool of prototypes, and there is a number of slots for each class. For example, in this image, each class has 3 slots, right? And those slots are at the beginning initialized randomly, and they have to learn which prototype should be put in each slot of the class, right? So first, there is the parameters which we again train the prototypical parts, right? There are parameters of the network, standard parameters of the network, like before. But additionally, we have to train the slots, right? The parameter of the slots. So we differentially, learn everything. The backbone network, the prototypical parts, and the assignment to class, right? And for this, we used few things. For example, first of all, we used Gumbel softmax trick to, well, make those classes, make those slots one hot, right? We also had to, we also wanted to differentiate between slots, so we did not want to prototype P1 be assigned to all the slots of the class. We wanted to assign different prototypes for the slots of the class. And we also introduced a specific focal similarity function, which tried to generate more salient prototypes. When it comes to the results, from the last paper, a lot of other approaches appear, like Proto3, testnet, and we had to compare to much more methods. That's why the table is larger. And well, what was the main achievement of our work is that it obtained similarly good results to the most recent methods, or better. In case of Cube, it was better. In case of Stanford Card, it was a little bit worse than testnet, for example. However, comparing to testnet, we had much less prototypes, because testnet does not share prototypes between the classes, and our approach shared it. And we also did user studies on the mechanical Turk, where we tried to answer which of the method generate the most salient prototypical parts. And you can see the comparison of our method, which is on the first column, with the two other methods. You can see that in this example, our method generates more salient features, but we also put much more examples and analyze it more statistically on the mechanical Turk. Because we really enjoyed to work with prototypes, we also tried to apply it to segmentation. So the idea was not to just obtain the segment of the object, but to obtain the, well, information about the parts of the object, right? This is the segment of the bus, but some of its parts corresponds to window, some of them corresponds to tire, and so on. And again, we had no extra information about the parts of the bus, right? In the training, we had only the upper information, right? So the image and the segment. And this is the architecture. However, what I think is much more interesting is what kind of well, prototypes we observed. For example, for humans, right? So here you can see class person and sorry, I think the cut is better here. So you have three examples of cut image, right? And 4 prototypes of class cut, right? And you can see that one of the prototype was responsible for the nose, right? One of them was responsible for the contour of the cat. One of them for the face, and maybe the body, right? So this way, we also could, instead of just returning the segmentation map, we could also say to which prototype all the pixels corresponds, right? which prototype activated most. So when I would talk about what I would like you to get from this lecture is that is how the prototypical part network work. And we spent, I think, an hour to explain prototypical parts. Of course, that in the end ended it in maybe less detailed description of the following paper, which my opinion is good to look at if you are interested in this approach. And the methods, the prototypical parts, well, are aimed to use deep neural networks which are self-explainable, right? And even though they are currently used in fine-grained scenarios, more and more works appeared to use them also in other databases. When it comes to my team, we are currently working in introducing this approach to various aspects, like unsupervised prototypical parts, right? How to obtain prototypical parts using, for example, self-supervised method, right? This is one of the direction. The other one is interpretable lifelong learning. So how to use prototypical parts in continual learning. Here we still wait for ICCV final decisions. We already have a paper in it. The next one is how to input interaction into the process, right? Because sometimes the prototypes are useless from the human point of view. So humans should be able to say that they should be removed, they should not be used during the training, right? So how to introduce the oracle, the human, into the process of the defining prototypes, and also how to introduce it in the tiny machine learning approaches, so where we have some limitation considering the memory, the central processing unit, and so on. So if you are interested in that kind of work, that kind of research, then please apply for open position, both on GMUM or ideas. And thank you very much for your attention.
Thank you very much for the interesting talk. And well, we have quite a lot of time for some questions.
Thanks for the talk. I was thinking, I'm trying to understand what is the role of having that elaborate training scheme. So are we incentivizing the network in any way to learn more interpretable representations? Because I went through this, let's say, thought experiment. If you can train your network in a normal way without any, let's say, changes to the usual way of training, then in one of the layers, let's say, you take all the features like you did, and then like channel-wise, let's say 7 by 7, and then you take each of them, and then you can put them all in a latent space, and maybe you can do k-means clustering on top of that, and then you can take the centers to be your prototypical parts, and then you can take the feature vector that is closest to the center as your, let's say, visually perceptible prototypical part, and you can try to explain the output of the network in that way.
Yeah, I think that that kind of approach has also appeared, but put attention that here you introduce the second step of the training, which is not differentiable, right? So
there's no training. Once the network is done.
Yeah, exactly. So network is done, right? But you have to run the clusterization, which is also a training, right? This is kind of training, right? Clusterization.
Okay.
So you generate clusters, right? And then you use them in inference. But how sure are you that those clusters are optimal? You have not used them during the training.
Right. But the clusters are on top of the features that are learned by the network.
Yeah,
so all you can do is try to explain. So the network during the inference time outputs something, says that, okay, this is this bird. And then just looking at the features for this input image during the inference time, you can map to the latent space that I was talking about, where you have the cluster centers, and you can then tell, oh, because of this, network thinks like exactly the same procedure.
Yeah, I fully understand. I think that it's possible, but I think it's also not optimal because in the end you use non-differentiable clusterization and then use those clusters in the inference. So at some point maybe you could, I don't know, use those clusters and again fine-tune the network a little bit to be optimal for those clusters. I mean, your loss function that you used before clustering does not have to be optimal for the cluster approach. You know what I mean? That you would have to somehow fine-tune the network after you generate the clusters also to optimize it better. But yeah, it's possible. But I would say it's a type of prototype approaches that appeared before. The question is, how would you use it for prototypical parts when you have many prototypical parts for one class?
I'm not sure.
Yeah, but yeah, it's possible. I would say, but suboptimal. I would also.
Right.
In my opinion.
So this training also incentivizes the network to learn more interpretable features in a way. So it's not only about saying why the network made some decision, but it's also about training network that is inherently more interpretable in its feature space.
Yeah, sure.
Okay, thank you.
One question here. A really interesting talk. First question, like the similarity matrix should be 7 by 7, right? Like why do the heat maps look more fine-grained?
Similarity matrix should be 7 by 7, and what was?
The heat maps, they look like more detailed than 7 by 7 pixels. And I was just wondering why.
So the 7 by 7 was just like example that 7 by 7 can appear on the last layer, right? Convolutional layer. But as we said, we could take feature from the previous layers, which are more detailed. So I think this could be one of the solution if you would like to have more detailed map.
Okay, but like your map also like looks very fine-grained. Is it just?
It's interpolated.
Okay, it's interpolated. Okay.
Yeah.
Okay. And a second question. The loss kind of also has to kind of look at all the other encodings, right, of a lot of other samples. Like how much longer does the training take with this specialized loss?
Well, the training, I would say it's the 1.5 of the standard network.
Okay, not that much difference.
Not that much.
Okay. And for these prototypes, you always just look at a couple of images, not the whole training set.
Well,
during training,
the prototypes try to, as I said, especially in this approach, when we introduce focal similarity function, right? We try to prototypes to look only on the specific one. I would send one of those 7 by 7 pieces, right?
Okay, but can you go back to the loss formula?
Loss?
Yes.
Which? The first?
At the beginning, yes.
At the beginning, okay. This one?
Yeah, exactly. Like the loss is like the x element x, right? Like, do you compare it to every other image in your training set, or is it you just take like a sample?
Well, we compute this loss for each image in the batch. Because
okay.
we compute cross entropy and this for the images in the batch.
Okay, so you only kind of compare to prototypes within the batch. And
Yes. Yes.
okay.
Yes.
Okay.
Yes.
Okay. Okay. That makes sense why it's not that much slower.
Yeah. Here I said that we take all. Sorry. Yeah.
I think it's just
X is from the batch.
Okay.
Yeah.
And also one question: did you ever try it on ImageNet or something?
Try what?
This method on ImageNet, or does it only work for images which are like very, very similar but have like just?
I haven't. But this year a work appeared which applies it to ImageNet. So I can send you email if you.
Okay, and it also had good results, or was it because I would think this works very well if like the class differences are like fairly similar and the class similarities are fairly similar between kind of the images, right? Like if it's more complex, it might be more difficult.
It works quite well with ImageNet, yeah. Like the paper that I talking about, the new one.
Oh, okay, thanks.
Yeah.
I had 2 questions. Thank you for the talk. My first question was like, what are your views on the validation end of interpretability? Like, we just have accuracy as a measure right now, but how do you compare interpretability versus what we humans perceive? And the other part, second question was like, what are the other approaches apart from prototypes that you would like to see them compared to? So maybe you can give some insights on them. Thank you.
Yeah. Well, when it comes to the evaluation, I think that a lot have to be done here. I think that some measures are very interesting, like for example, the measure who tries to analyze how the explainability changes when we make a perturbation of the image. So how stable is the explainability, right? But those are usually the metrics which are somehow automatic, and we are not certainly sure if they measure the stability of the model that we explained of the explainer. So I think that well, we should go into the direction of some benchmark which would contain the number of biased, for example, biased models, which we know that what they use for, what they really use for the prediction, and then analyze the explainability method based on this benchmark. So instead of using one model and some database, to analyze the explainer, we should use a lot of models to analyze the explainers, right? So the input should be different, right? And right now it's not like that, right? In my opinion, it should go into that direction. And the other methods of interpretable methods that appear, this is hard. I mean, do you know some?
No, I am not aware of. So it's when we talk about self-explanatory ones, like apart from prototypes, do you know any of them? Even I don't.
I mean, it's really tough. I know that there is a lot appear in the domain, like non-visual domain, right? Like the tabular data and so on. A lot of methods appear there which are interpretable, but for visual data, lately I did a research and on related works to one of the grants, and I have problem with finding something like that. Maybe that's why the prototypical parts are grows so fast. But maybe some of you know it, so please.
Thank you.
Thank you.
So I had two questions. One is kind of a follow-up. So do you think this method could work with other kind of input data than images?
Yes, in fact, people also used it for chemical data, like graphs, when they created a subgraph. Even in my team, if you look on the work of my team, you could find it. And also on language data, yeah, there are many applications. And medical data.
And
also.
One last thing, like neural nets kind of learn some kind of implicit representation that we humans don't really see in the data, and that I think it's really powerful and really interesting. It could also give us some other kind of understanding that we cannot get alone as humans. So don't you think that this kind of approach kind of prevents us from having a deeper understanding of the data, or do you think it's the other way around, that actually being able to comprehend it in a more precise way actually makes us understand the data in a better way?
This is hard to say. I think that again it's somewhere between. That's why I thought that our next research also introduced human into the loop, because I think that especially for domain expert like medical doctors, we should first use their knowledge to generate prototypes and then introduce new ones to show them that our method tries to use their knowledge, and when they use their knowledge, it obtains the following results. But if we introduce additional prototypes, right, we obtain better results. And what do you think about those prototypes? Because then it would be much simpler to gain new knowledge about the world, about the data, right? Especially in the expert domain, right?
Yeah, that might be very, very interesting. Like, for example, I don't know, you're classifying tumor cells, and the domain expert gives you a bunch of examples, and then the AI gives you another example that the domain expert didn't consider, and they say, oh, actually, that might be a tumor as well.
Yeah, but again, the AI should first look on what experts said, right?
Yeah, exactly.
Because otherwise, there will be a wall from the expert side, as I observed in my research, right? They first has to know that something is what they know to gain new knowledge. If we give them completely different, completely new prototypes from the beginning, then they will probably reject it, and no knowledge gain will be observed.
Thank you.
So my question is less on the science and a bit more on the engineering. So how much does pre-training help in this kind of architectures, like the CNNs that you're using in the initial parts of the architecture? If you use some, pre-trained VGG or something, does that help? Do you do that?
Yeah, so the pre-training is very important here. And so we observed that we obtain much better results when we use network pre-trained on naturalist instead of ImageNet. So I would say that the important thing is the both architecture and database, but database even more, right? Also, we thought about transformers, but the problem is with transformers is that they do not have this property like convolutional network, that the information about the token considers the information from the input, right? Because there's everything mixing inside, and there's a problem. So it was problematic to apply prototypes in transformers.
Thank you.
Have you ever thought about doing some sort of hierarchical prototypical parts? Because I feel like you have like 200 classes, and you said like if you have like 10 prototypical parts per class, then you have a lot of these parts, and you try to have these techniques to reduce the number of the parts. But for example, in a data set where I have completely different classes, like, I don't know, airplanes, cars, but then I have different classes of birds, and then, for example, really different kinds of birds, it would probably make sense to look at the first part actually like, just like, I don't know, are there eyes or are there wings? And if yes, then I need to like distinguish on different properties of this bird. So you could drastically like reduce the number of parts you actually need to have.
So the question is, have I considered hierarchical prototypical parts? I haven't, but I think I saw some paper on this topic. Like I mentioned Proto 3, which is not a hierarchical approach. It's just a tree which inside the nodes contains a prototype, but the hierarchical prototypical parts, sorry, cannot tell more about them. But please look on the Google Scholar. Yeah. I think that there is an approach to it, but not some very famous. I think it's a good idea to do it. That's for sure, if not done yet.
So I have a question related to the fact that this kind of application can be surely used in industry, especially for fields that require a certain degree of safety, like autonomous cars. But at the same time, many of these applications work in real time. So they also need the speed and accuracy to work well. So my question was, can we have explainability and also speed and accuracy, or do we have to make like trade-offs to also have explainability?
When it comes to the inference phase, this network works similarly fast, like the standard network. So I would rather, one of the questions, as I said, is how to apply them into tiny machine learning, like the problem of when we need fast, right, fast processing with some limited power, right? So this is an open question, and we want to work on it right now, especially on ideas when my team is dedicated for such things. I think it's very interesting and important. So I think it will grow right now.
Okay, thank you.
Okay, last question.
I was thinking, have you looked into how does this approach play with different scales of objects? So in the bird classification task, I can imagine that you can have a close-up image of a head of a bird. Then your output is not going to make sense.
Yeah. So I would say that in a standard form, it would work terrible for the different scales. So that's why different extension, different approaches try to modify it. So it works for ImageNet, for example, right? And again, I will go back to this paper that uses an ImageNet when the scales are different.
Okay, thanks.
So it's happening, right? People do it, but in the standard form, it wouldn't work. Thank you very much.